So yeah, so we saw electric flux. Through a surface S, E dot dA. We saw Gauss's law. If you have a closed Gaussian surface, then you can say that the flux through that entire Gaussian surface will be equal to charge enclosed over epsilon naught. On Friday, we saw how we can deal with not only lambda, but sigma and rho. So this was surface charge, density, volume charge density, and if you watch the video, you learned that in electrostatics, in the material of a conductor, what can we say?
The magnitude of the charge in the tilde 0.
What would be zero?
The magnitude of both the charge and the electric field in that.
Yes, yeah. So the magnitude of so the electric field will be 0 in the material of the conductor, and we also know that any charges that are on the conductor will be on the surface of the conductor. So charges surface of all right. If you haven't watched the video, please do so. All right, so let's get some practice with that. Go ahead and grab your little paper clickers. After we've done this last bit about Gauss's law and conductors, then we'll move on to electric potentials. Turning on. Show me your votes. Okay, all right. Cool. So mostly for B, B is correct. Emma, you want to give a shot at explaining?
Yeah, sure.
Oh, I said Emma. Oh. That direction, yes, but
Honestly, we were not totally sure.
that's all right.
But my gut reaction
Uh-huh.
is that the inside charge is -2.
The point charge, yes. Okay, well that's given to us that it's negative, yes.
And so the inner surface, I was thinking of something to do with canceling that -2, so it goes to +2.
Okay, true. Yes, that is correct. And all right, so let's figure out why it has to cancel out. And I have a hand from Alex here. Yes.
So since the charge on the inside of the hollow pointing in
Yes.
towards the charge. So because it's negative, the positive charges are going to collect on the inner part
Sure.
of the sphere. And since it's metal, so we know it's going to be a conductor.
Yes.
A good conductor. Then the positive charge will be getting to pile closer and closer to the center, while the negative charge will want to go further and further towards the outside.
Sure.
And eventually, the electric field being caused by the positive negative charges on the hollow sphere will cancel out with the field being caused by the charge inside the sphere.
They will cancel in the material of the conductor. Yes, that's right.
So therefore, because the field cancels out with the field on the inside, it will have to be a positive 2.
There's a bit of a jump there. You're correct, but there's a bit of a jump there. Yes. Anyone want to fill in the details exactly how we know that it's +2? It makes sense that it's positive charge. It makes sense that it has to arrange itself to cancel out the field. Louis. Yep.
Inside, there's 0.
When you say inside. Oh yeah, yeah, in the material of the shell. This, yeah. This,
So in order to have a 0 field inside the shell, there needs to be a +2 on the inner surface that can't draw like an imaginary.
Okay, now you're filling, because until then you were saying pretty much what Alex has said, but now yes. So how do we use Gauss's law to fill it in? Okay, so yes, we draw a Gaussian surface in the middle of the shell. Okay.
Then you know that it has to be 0.
What has to be 0?
The
The field going through the Gaussian surface. So if we draw a Gaussian surface here, right, the field has to be 0 because we're passing through the material of the conductor.
And then you know the charge and flow.
Right. So Gauss's law tells us, well, first by the definition of flux, we can see that if the electric field is 0, the flux is 0. And then Gauss's law tells us, oh, if the flux is 0, the charge enclosed must be 0. All right. But enclosed by our Gaussian surface. So if we drew our Gaussian surface here, and that is how we ended up with the field being 0, what charges is it enclosing? It's enclosing this charge, and it's enclosing whatever's on the inner surface. So the sum of those two has to be 0. And so yes, your gut reaction there was right, they have to cancel out, but this is how we can rigorously prove that it has to be +2 on the inner surface. So,
Where does the rest of the +5 go?
oh, excellent question. Well, okay, before we get to that question, let me ask you this. Okay, and show me your votes. Yeah, it's clearly not uniformly distributed because this is off to one side, so clearly there'll be more positive charge on this side and less on this side. Okay, now I think we come to Cyrus's question. All right, yes, it is C. Yeah, and so Cyrus asked, where did the rest of the charge of the +5 go? And so we know that for conductors, the charges have to be on the surface, on the surfaces. So it either was on the inner surface or the outer surface. We know how much is on the inner surface. We know it's +2. So the remaining +3 has to be on the outer surface. Question, yes.
Is there still no electric field even though it's
No, so there is electric field here.
right, but like inside?
In the material, no, there is no electric. Yeah. So that is the thing about conductors is because charges can move in the conductors, they rearrange them. They keep move as long as there's an electric field in the conductor, the charges will move, and they produce their own field. That induced field, the field that they produce, will progressively cancel more and more of the external field until eventually they perfectly cancel out. And then there's no more reason for the charges to move. So they stay in that configuration. Margot.
So I get how the field is canceled on the like inner surface the shell.
Yes.
Wouldn't the charge on the outer surface?
Excellent question. So yes, so if we have a charge on the outer surface, wouldn't that produce its own field and that produce a non-zero field here? Excellent question. So let's. Well, let me ask you this before I answer that. Let me ask you this. The charge on the outer surface, uniformly or non-uniformly distributed? Right, show me your votes. Okay, mostly for A, yes, it is uniformly distributed. The reason it's uniformly distributed is, and I know this is sort of circular, but we've said that there's no electric field here, right? So the outer charges don't know that, oh, things were non-uniformly distributed here. They say, okay, no electric field, let's just repel each other. And so they repel each other and distribute uniformly. But even then you might say, okay, we have a uniform sphere of charge. How does that not produce a field? So let's take a look. So, close enough. All right, so say we have a uniform spherical shell of charge. Infinitely thin shell, so it's just the surface of a sphere, and the charge is spread uniformly over that surface. And say we want to find the electric field. Well, it's nice and symmetric. What kind of symmetry does it have? Spherical symmetry, which is one of the special symmetries that we can easily use Gauss's law for, right? So remember that Gauss's law is always true, but it becomes particularly easy to use when we have either spherical or planar or cylindrical symmetry. So in this case, we have spherical symmetry. So I'll draw a Gaussian surface. I want to find the field inside, so I'll draw a Gaussian surface with the same symmetry. Right, so it's also a sphere with the same center. And I'm trying to find the field at some point on the sphere. So let's say I'm trying to find it at this point over here. So now I apply Gauss's law. So it says, okay, flux through the Gaussian surface is Q enclosed over epsilon naught. Because it is spherically symmetric and this charge is uniformly distributed, we know that if there is a field inside, it either has to be pointing all inward or all outward. Right? And then because I've chosen a Gaussian surface with the same symmetry, we can see that this integral, E dot dA, simplifies to just E dA cosine theta, and the theta will be either 0 or 180 degrees. Let's assume 0 for the moment. So cosine of 0 is 1. Electric field will be constant on that surface. So I can pull it out. So this just becomes E times A, which becomes E times 4 pi little r squared, where little r is the radius of this Gaussian surface. We'll call big R the radius of the sphere of charge. All right, so we have this, and now applying Gauss's law, we have E times 4 pi little r squared is equal to Q enclosed of epsilon r. But how much charge is enclosed? 0, right? Nothing is enclosed by this orange sphere. All the charge is outside. This would be 0, which tells us that the E field is 0 if you have a uniform sphere of charge. Question, yes.
In the hollow sphere case.
Yes.
With the charge inside.
Yes.
If you like don't have enough charge in the conductor to.
Oh, no, so the idea of conductors is that we assume that they have, I mean, like, even if you started out with a neutral conductor, right? It's not that it has no charge, it's that it has equal amounts of positive and negative charge. So if you started out with a neutral conductor, what would happen is it would polarize and you would have +2 on the inner surface and then -2 on the outer surface.
But what would happen if there weren't even enough electrons in the?
Then we wouldn't call it a conductor. So, but no, I mean, it's a fair question. We're idealizing the conductor here, that it has enough electrons which are free to move, that, yeah, it can accommodate any polarization. But, yeah, that's true. It's an idealization of it. Yes.
What would happen if you like grounded the shell with the charge inside? Would it just be polarized with +2 on the inner surface and minus in the outer surface? Or would it?
So if you grounded the outer surface, if you grounded the shell, this would still attract +2 to the inner surface, but now the charges in the outer surface would run off to the earth. So the outer surface would become essentially neutral, and yeah, you'd have +2 over here. And then if you cut the grounding, then you still have the +2 on the inner surface. Yeah.
And nothing on the outside?
And nothing on the outside, yes. Other questions? Marco, so does that answer the, okay, good. All right, so this is actually one of two what we call shell theorems, which was something that Newton actually showed in the context of gravity, but it's basically what happens if you have a shell, uniform shell, in this case of charge. For Newton, he was just considering mass. So never remember which one is theorem 1 and which is theorem 2. Let's just say, sure. Theorem 1, inside a uniform shell of charge, E equals 0. Right? And that's anywhere inside. So not just at the center, where clearly at the center by symmetry you can see that, oh, all the fields would have to cancel out. But we're saying anywhere inside the field is 0. However, we also have a nice result if we go outside. So outside the uniform shell of charge, it produces the same field as point charge. Spherical shells are quite nice that way. Inside, the field is 0. Outside, you can instead collect all that charge to the center and imagine that it was just a point charge at the center, as long as you are outside the actual shell. Of hands. Samuel, then Freddie, then Angelica.
Do solid spheres also behave the way theorem 2 says, where they behave like a field charge? Because logically you would think so. Like a point charge, yeah.
Right. Yeah, no, solid shells also, because you can build a solid shell out of several hollow ones.
Okay.
So yeah, outside a solid shell or solid sphere, you could treat it like a point charge. Yes. Freddie and then Angelica.
So I want to ask something similar. So is this specific to sphere, or can I have a cubical shell and then does sphere need to still hold?
Oh, a cubicle. Oh, no, it won't hold for a cubicle. Yeah. So, yeah, you need the symmetry of, well, you need a symmetry of a sphere. For the easiest case, you could have a cylindrical shell. If it was an infinite cylinder of charge, then yes, inside there would be no field there.
That was my question.
Okay, all right. Sorry.
Each side is a uniform shell charge, each side of the material, right?
No, sorry, in the cavity.
Oh.
Yeah. Oh, Max?
So when it's treated like a point charge from theorem 2, for the part of the equation that requires R,
Yes.
is that from the center of the sphere?
Yes, that's from the center. There?
When you apply this to gravity, it's basically just like a planet with like a hollow shell and like a hollow material like gravity.
Exactly, yes. When Newton applied in context of gravity, well, he was doing two things. One, he was saying that, oh, if you're outside the Earth, then you can just treat it like a point charge at the center of the Earth with all the mass of the Earth concentrated there. But also the curious side effect of, oh, if you had a hollow Earth, and goodness knows there are conspiracy theorists who think there is a hollow Earth. It turns out, however, that the field inside, if it was perfectly uniform, would be 0. But I do need to emphasize, this is because of the perfect spherical symmetry. As soon as you disturb the symmetry, if you put like one extra charge here, then, well, you can subtract out the uniform shell part, and whatever remains, whatever non-uniformity remains, that will be what's causing a field inside.
Isn't the Earth not a perfect sphere?
That is true, yes. Well, it's also not hollow, so it's a moot point, but other questions? Okay, so yeah, so these are handy just to simplify lots of situations. Okay, I think that is good enough for Gauss's law with conductors. So now we will move to electric potential energy. All right, so I remember Kyle asking a few, I think last week sometime about like, oh, is the electric force a conservative force? Yes, it is. The electrostatic force is a conservative force, and we know that all conservative forces have associated potential energies. And energy is a scalar quantity, which makes it very easy to handle compared to vectors. So we start with the idea of electric potential energy. And we typically use the symbol U for this. And we'll start with the idea for if you have 2 point charges separated by a distance, what is the potential energy? So if you have Q1, Q2, separated by a distance R, and what will be the U for this situation? you a moment to write stuff down. Let me know if ever I'm like erasing stuff or covering stuff up too fast. Oh, sorry, can't read it.
Is potential energy a vector for?
Well, no, it's a scale. Well, energy is always a scale. Question 5.
Usually these look pretty close to what we see with gravity. But
Yes.
in this case, it's not like MGH.
Oh, well, that's because you haven't seen the proper form of gravitational potential energy. MGH only holds near the surface of the Earth. It's a great question. So if you want the potential energy of gravity, the true form, which holds for like any two masses, is
Okay.
yeah. That's insightful. Yeah, you would expect. I would think so far as exactly as you said. There's a lot of similarity between gravity and electromagnetism. The biggest difference is that charges come in plus and minus, but mass only comes in plus. Yes.
Is the process for getting there the same as the one for the electric force, like bringing in a mass within
The process for getting.
that equation?
Oh, this one. Yes. Yeah. Yeah. Samuel, and then over there. Yes.
So if gravity changes to MGH at the surface of a or like on the surface of a strong gravity field, is it the same true of an electric field? If you're on the surface of a strong electric field, it changes to something like QKH or something like that.
So it's not so much that it changes to MGH, it's just that MGH becomes a good approximation.
Okay.
All right. So it's for gravity, it's like it's always this form, right? It's just that if you have, this is a sidetrack into gravity, but it's useful to know. If you are near the surface of the Earth, you can write your R as basically radius of the Earth plus a little bit h. Okay. And so that if you plug that in, so then you get, okay, U gravity equals minus G mass of the Earth, mass of the object, divided by radius of the Earth plus h. And typically the heights that we're looking at are much smaller than the radius of the Earth. So we can use well, what we can do is we can pull out radius of the Earth. So we get minus G and pull out radius of the Earth. We get 1 plus h over RE. Is it going to take? No, okay. And what we can do then is an approximation. So the approximation that we do is if you have 1 plus x raised to n, and x is much less than 1 magnitude x, then you can approximate this as 1 plus nx. This is one of our, as a physicist, is one of our favorite approximations. You can either think of prove it using either the binomial series or using Taylor expansions. It comes up in a lot of places. So here the idea is that our x is h over RE, and yes, typically the heights we're using are much less than the radius of the Earth. So this is quite small. This is a good approximation. So I could write this as this times 1 plus h over RE raised to minus 1. So you get and then roughly it would be 1 minus h over RE. Multiply this through. What do we get? We get this term and then plus G M E M H over RE squared. This does not depend on height, right? So it's essentially constant. So we can neglect it because you can always choose your zero potential energy to, eliminated. Here, what do we have? We have M, we have H. This is your little g. Okay, so this term is your mgh, and so you have g me over re squared is g. Little g. Question from Billy. Yes, what is the units on page? Oh, you could figure it out over here, because you have joules on this side, you have kilograms here, you have meters here. Move it around a little bit. Caroline, don't worry, I haven't forgotten your question. But yeah, so this is why when there was an experimentalist, Henry Cavendish, when he finally determined the value of big G, they said that he had weighed the earth. Because once you knew big G, people had easily, long before, measured little g. And even the ancient Greeks knew roughly what the radius of the earth was. Once you know all these three, you know the mass of the earth. So, yeah. So yes, there was a digression, but useful one, because it shows you stuff that you will see in physics later on. Yeah.
So if electric potential energy is dependent on charge,
Yes.
does that mean that it can be a negative?
Yes. Yeah. Depends on what Q1 and Q2 are. Exactly. If both are positive, then it's positive. If both are negative, then it's positive. But if one is positive and one is negative, you have a negative potential energy. And we can see that it does have, okay, it's proportional to 1 over r. So yes, if they go really far apart, the energy goes to 0, which is what you hope for. Other questions? Yes.
Is there another equation for u? Because this one seems like a derivative of Coulomb's force.
Yeah. No, exactly. Brilliant question. So I'm going to cover up this part. Is that okay? Yeah. Okay. So what did we learn in 113 about the relation between conservative forces and potential energy? We learned a couple of things. One was that if you have potential energy U, you could take its negative derivative to get the corresponding force. Right? So this is using the full calculus notation, but if you wanted like Fx, that would be minus partial U partial x. Fy would be minus partial U partial y, and so on. So yes, this is exactly what's happening here. If you know that the electrostatic potential energy is this, you can take a negative derivative and end up with the force being this. Right, because when you take derivative of 1 over r, you get minus 1 over r squared. But there's an additional minus sign, so the minus goes away. And then, yeah. So yeah, the potential energy leads directly to Coulomb's law, like this. The other thing, did that answer your question? Other questions? Okay. Oh yes. The other thing was we learned that the work done by a conservative force is negative delta U. That also still holds even in this case. It will be useful when we look at work done by electric fields. Yes.
What is the upside down delta?
Yes. It's called the gradient. If you go into multivariable, see the bit more. But basically, it's a bunch of derivatives. So if I wanted to write this out, it would be basically vector is so it's sort of a shorthand for doing like 3 derivatives and like matching them up in the directions. Questions? No? All right, so we'll do a few more multiple choice questions. Yeah, okay, let's do a couple of questions. So configuration 1, your charges Q1, Q2, separated by distance d. Energy is -4 joules. What is the energy in configuration 2? Very quickly. Get ready. Show me your votes. So B, yes, we have doubled the distance, and so we have the energy. So if it was -4 built before, now it is -2. Right? It's going to get closer to 0 as you go further and further away. Yes. The hint is I've told you how to handle pairs, so just treat them as a bunch of pairs. All right, pretty unanimous for D. D is correct. Anyone want to justify it? Let's go Max, Limit.
All right, so what I figured is that like the net potential energy of the entire system is just like
That is correct, yes. So just laying it out in more detail. It's a job. Yeah. +2 Q squared, so total of -4 so far. And then we have another -3 Q squared here. So -4, -3, -7 KQ squared over here. All right, that is it for today. Yep.
Initially there is like a positive and a negative. If we put no matter a positive or a here